Okay, everyone, I'm quickly going to share my desktop with you again, and we're going to go over the presentation which I prepared for this. Okay, let's just escape this one. Okay, so the subject I'm going to be talking about is why is the holistic approach needed for retrofit, and explain this through some dynamic simulations. This is me down here, this picture of me, and my role, as Safa mentioned, is the project management of this, the HERB project, and I work at the University of Nottingham. And this is funded by the 7th Framework Programme. So, some content. This is going to be available to everyone at the end, so I'll briefly flash through this because we're tight with time. And so, obviously, I'm going to go over some research background, introduce the dynamic simulation example, and go over some results, and then justify why the holistic approach is useful. So, just to give some background, ultimately, if we look at the European energy consumption, around 40% is consumed in energy is consumed in our buildings. This falls in line with the industry and household use. Looking at that in a bit more detail, the building stock, roughly about 25% is non-residential, but the residential stock accounts for the majority of that. And looking at the age of the stock, you can see here that roughly between 35 and 42% is aging and outdated, just dependent upon the location, with the north and west having a significant portion of its stock very old. Now, our overall aims with Retrofit are ultimately these 3 points. We want to take sick buildings which affect our health to happier buildings and make them greener and better with energy consumption through reduction of energy usage overall to around 80% and reduction of our emissions of carbon by 60%, which is what we want. Now, I work in the UK, so now everybody is coming from a particular location, but in relation to the UK houses, these are just some typical examples which we have. These houses here were constructed around the 1900s, and these were constructed in the 1960s. But semi and terraced houses are roughly account for around 2/3 of our building stock. That's 2/3 of 21 million homes. Now, if we take the current retrofit approach, what is used in industry, ultimately, if we're going to aim towards this 80% energy saving, we're going to look for a number of measures which will enable us to do that. Now, currently, the way it's done is piecemeal. Someone will take a particular measure, whether that be an insulation, loft insulation, or the changing of windows, and apply that, and they'll go for the simplest and cheapest method that is available to them to get more bang for the buck, effectively. So you'd expect there to be measures up here which are more effective than measures down here, but that begs the question, what measures should be applied that have the most impacts, and where do we start from? Well, ultimately, from a holistic approach, within a project, we have the opportunity to look at this as a whole, and we also have the opportunity to utilize specific tools. One of these is to utilize computer models. Now, this is quite unique because from this we can start to analyze what are the climatic impacts in relation to control, components, static components, such as the items which Safa mentioned, but also there are socio-economic impacts, to the occupants' well-being, and then the well-being of the entire community. This will be mentioned on later. Now, in relation to the establishment of a starting point, this is a bit of a grey area because one of the main questions which was asked in our project, where do we start from? What is the baseline? What do you base your 80% saving on? Well, if we look at the past century from when the houses were built, they're in the 1900s, there have been like 4 significant periods which have actually affected our houses, these being the World Wars and the energy crisis which has currently occurred. Now, if we look at this in detail, ultimately, with the World Wars, we had a massive loss in skills, and we also had a baby boom afterwards. So post this period, there was a massive requirement for houses, so they were constructed very, very quickly. But also, we didn't have the skills available, and to construct them, so the standards fell. Now, around this area here, we have this mass installation of gas-based central heating systems. Excuse me. Now, this era here is similar to when the mobile phone was applied to what we had with the landline phones. You see, energy use all of a sudden became very cheap and readily available to everyone. Now, around this area here, we had the establishment of the building regulations. So rules started to come in with the construction of houses because of the massive increase in price of energy. And then obviously we had the Kyoto Protocol, which brought in the energy company legislation, where energy companies in the UK, for example, were required to save carbon savings. So this has led to a mass installation of insulation in the UK and many other countries. Now, if we take a starting point, the most logical point would be here, and this is based upon what a survey which we did of 6 properties in the UK. Now you can see here, when they were built, solid fuel would have been used. There would have been only single glazing, and no insulation would have been used throughout. But since then, you can see here that obviously the boilers have been upgraded because it was cheap to do so. In a number of cases, the double glazing has been done because it was both cheap and fashionable to do so. And no insulation has been applied; it's too expensive. And loft insulation has been applied in a varying degree, and the thickness will reflect the time in which it was done. And obviously we have low energy light bulbs, but that is entirely dependent upon the occupant. Now, what you have to remember is these measures here are the low hanging fruit, but this is rapidly running out. So in relation to retrofit, we have to look at other measures. Now, for those of you that undertake building simulation, this is just an example of the model which we constructed, and I used Design Builder, which is a commercial software, and Energy Plus as the compiler. So it's a very sophisticated academic piece of software. I won't go into details though. And we basically looked at 3 parameters. We took the baseline, and I'm not going to go into these in massive details, but we also looked at the reality case where we were now, and then we looked at an aspirational case, essentially a retrofit case. Now, the areas here which you want to highlight are the set points, 18 degrees being the heating set point and 25 degrees being the ventilation set point. This will be applicable later, but also air tightness. You know, when air tightness is improved, it's normally to do with an improvement in the fabric, and with application of insulation, this is likely to occur. So we made this assumption. So just looking at some results, you can see here, this is the as-built comfort results. So this is what would have been used if we simulated the building as it was constructed. This being temperature down here, internally and externally, and this is being energy use in terms of gas usage and electrical usage here. Now, when we look at the reality case of what has been done so far, so this would be like loft insulation and double glazed windows, the areas which you want to be aware of are these points here. Now, this area here is what we want to improve because people are too cold, and this area here is what we want to be aware of because overheating can be a comfort problem as well. Now, when we apply the current measures that have been done on a survey, you can see here that there is a reduction in the energy usage, only minor though. And we also have improvements in the internal conditions, but the cost of that is still too high. Now, when we apply insulation, you can see here that there is a massive reduction in the energy consumption. However, if you look here, the internal conditions are actually compromised, only minorly, but we're still getting this overheating aspect here. And also here, there isn't much difference in the internal conditions in comparison to the other ones. So this is an impact effect which has come from the application of insulation, which can cause problems later on down the line. Now, if we look at the energy losses and what occurs, there are essentially 2 areas you want to be aware of. Essentially, this is the winter balance here. So you can see here in the winter we're having lots of losses through the walls, significantly, windows, the infiltration, the loft, and this here shows how much energy is used to balance that. Now, when we look at what's been done in the reality case, the easy areas are applied first. We've dealt with the loft and the glazing insulation, but this hasn't essentially dealt with the problem here, which is the wall losses. Now, when we apply insulation, you can see here we've dealt with the problem. There's a nice balance in the winter. but all of a sudden we have a summer imbalance. Now that can cause us problems later on, because that will have to be dealt with either through mechanical ventilation or air conditioning, which compromises our energy saving. This slide here just goes into details regarding the potential savings which can be made. So this is based upon assumptions, and if you have questions on these, please send me an email. I can go over the model in detail with you if you'd like. And this is the potential savings which can be made with just through loft insulation, and you can see here around 9%. Now, if we apply double glazing, you can make a further 10%, which takes the total cost saving down to this much. And now the massive savings, as you can see, have come through the application of insulation. Okay, now I'm just conscious of time, so I'm going to quickly run through this. Now, looking at this as a holistic viewpoint, previously we thought it was this way. However, in fact, it's not as easy as that. When we look at this holistically, you'll notice that the arrangement of these changes, because the loft insulation and low energy lighting, actually the savings which you can make with those don't cost a significant amount. So you want to focus on these first, because they're below around £50 in this example. Now, in relation to solid wall insulation, you're looking at a little bit more of a saving, around £200 per 1% energy saved, whereas high resistance windows actually cost more. Now, in relation to the other points you will need to apply in order to make the additional savings required, who knows how much that's going to cost. Which begs the question, are there other options we can use down here, such as the introduction of shading or new innovations or control systems? In addition, if we have to bring in ventilation and cooling, our savings can be compromised. But also, this doesn't actually quantify the socio-economic impacts. So, looking at the analysis, these are some conclusions. I'm not going to go into these in specific detail, but ultimately, what we want to remember is that we have to approach the problem holistically. Looking at it piecemeal does not work. In addition, our control systems might not be good enough. We're going to have to be bringing in some more sophisticated, but also quantifying what the socio-economic impacts, impacts to well-being, etc. So looking at this, post my analysis, the socio-economic impacts are going to be introduced by Philip Bristow. He's going to go over those later. Professor Riffat already covered a number of the building component impacts, but also Adrian Parker is going to go over these with respect to vacuum insulated panels. Finally, Walter Borsboom is going to be discussing the control systems which we are developing. And thank you very much. My email and website which we are developing is currently down there.